figure out calling you.
Okay. All right. Well, let me get it all set up first.
Okay.
Okay. Okay. I have decided to build a 4-transistor AM superheterodyne receiver with EE241L audio amplifier. Now, I've always wanted to build one, and this is very exciting to me. This is something I really enjoy. I actually did pretty well, and it came out pretty good. Now, there was a reason for the superheterodyne design. Previous designs, we had the crystal set, which is a simple tuned circuit and a diode detector, envelope detector. A more complex design was a TRF receiver, which included multiple tuned amplified stages, but each stage had to be tuned manually. And then a regenerative, super regenerative receiver uses feedback, positive feedback to regenerate the signal. Basically, it's actually pretty complicated, but we won't go into that. This is the basic crystal set right here. This is a basic block diagram. It has a bandpass filter and diode detector. Basically what it is, it's a resonant tank and a diode detector. High impedance earphones or headphones, because this is powered directly from the radio waves themselves, and it is very very low level. Probably. The next set, the tuned radio frequency receiver has typically had three stages of filtering and amplification, and each stage had to be manually tuned. So when you wanted to tune a station, you would have to tune the stage closest to the detector, and then you would tune the other two stages, and it was very hard to tune. So later designs, each adjustments were mechanically ganged. This led to the superheterodyne receiver, which actually it was kind of discovered by accident. It was a fellow named Edwin Howard Armstrong. He was one of the early radio pioneers, and in his early days of radio, this was when radio was just coming onto the air. AM was a big dominant player, AM broadcasting and also communications. He discovered that various tubes, when you input two signals into them in a special way, that they would mix, that these signals would multiply, and a multitude of different products were produced. And one of them was a lower frequency. So the mixer functions as a frequency down converter. So in the basic super heterodyne receiver, you have the RF filter or tuned stage. You may or may not have an RF amplifier. This does not. You have the mixer. So the RF signal goes into the mixer, actually into the base of the transistor, and the local oscillator is mechanically ganged to the RF filter. Both capacitors are mechanically ganged, and the signals are mixed, and a lower IF frequency is produced. And the reason for that is it's easier to design an amplifier to perform at a specific bandwidth or a lower bandwidth than it is a large range of bandwidths, like with the tuned radio frequency set. You had amplifiers that were performing all across the band, and there was inconsistent gain, noise, and things like that, and it didn't work really well. But when you have amplifiers that are tuned at a specific frequency, you can keep the gain constant, or at least how you want the gain to be. And then after the IF filter, it goes into a demodulator, which in this case is an envelope detector. Then after that, the audio amplifier. These are some examples of super heterodyne receivers. This is a transistor radio that I own. You'll notice this section here forms the local oscillator and the to the RF filter. This section here is the IF strip, and we have a diode detector on here and the audio amplifier here. This is a more modern one, and all those transistors are on a chip, and that's the audio amplifier that I use. It's kind of hard to see. So this is the schematic. This is what I use. So what happens is we have two voltages. We have the battery voltage right here, which is 3 volts from 2 AA batteries. This 2.2K resistor and these two diodes form a voltage regulator. That 33 microfarad capacitor there and there keep the voltage stable. And I will start with this part of the signal chain. So you have the AM antenna, which contains 2 coils or 2 windings. This large winding, this is the RF winding, and the one gang of the tuning capacitor and this form an RF winding. This is how it's tuned. When the capacitance is adjusted, the resonant frequency changes. And that signal is then coupled magnetically into the mixer winding. At the same time, we have another tuned circuit, the primary winding of the oscillator transformer, and this capacitor forms another tuned circuit. That forms the tuned circuit of the local oscillator. Now, with every oscillator, you need to provide energy to get it going, well, to start it. So energy is initially provided with this transistor, starts the oscillations going, and the oscillation is fed back to sustain oscillation, to keep it going. So those two need to be working. And what we're looking to achieve here is mixing. So it goes into the mixer transistor. And the the oscillator output is coupled to the emitter of the mixer transistor. The RF, mixer winding that contains the RF is coupled into the base. It performs, well, mixer theory is kind of complicated, but how it basically works is through intramodulation distortion. It creates many different products, and one of the products is the local oscillator frequency minus the RF frequency, which is the intermediate frequency. So the modulation product, the modulation that's on the RF frequency, is mixed in with the local oscillator frequency to create a lower IF frequency, which then is much easier to handle and amplify and filter and deal with. So this is an IF transformer. It's actually that right there. This is basically another tuned circuit, but its resonant frequency is around 455 kilohertz. So, and that's the intermediate frequency, and it's adjusted during alignment, so its center frequency is at 455 kilohertz, and that's very important. If not, then it's not going to be very sensitive. Then the signal is coupled to the other side, the other winding, fed into another IF amplifier. These two components set the gain of the IF amplifier, and is also further filtered again. Then it goes through one more stage of IF amplification and filtering, and then finally reaches the detector. Those two diodes through rectification, they are the envelope detector, and they rectify the IF signal, and so in this case it only leaves the bottom half of the signal. So to extract the audio out of there, what you need to do, this 10 nanofarad capacitor filters out the carrier component, and that leaves you with the audio. Now, the good thing about a super heterodyne, one of my favorite elements of it, is there's automatic gain control. And how that works is that the audio signal, this is a filter, and this 10K resistor and 33 microfarad capacitor act as a filter, and what it does, it'll produce a varying DC voltage according to the audio signal. So that varying DC voltage is fed back to two areas. It's fed back to this IF amplifier, the first IF amplifier. If there's a strong station, what it'll do is it will cut back the gain. So if the volume is very loud here, this will produce a lower voltage. It's inversely proportional to the audio signal coming in. So that'll produce a lower voltage, which causes this transistor to kind of cut back and amplify a little less to maintain a constant audio level. It's also fed back to the mixer transistor, and what that does is when you feed it back to the first IF amp and the mixer transistor, you have a better range of this automatic gain control. That's why there's two. And then once the audio signal is kept constant and demodulated, goes into the audio amplifier. This is a schematic that I drew up from the bridge mode test circuit in the data sheet. And these capacitors are basically what the data sheet recommends. There are basically decoupling capacitors. This this RC shunt here and here is recommended by the data sheet to quell any parasitic oscillations. In my experimentation, I found that the original 10 microfarad decoupling capacitor on the supply pin was not enough, and the amplifier oscillated. So what I had to do was I had to add more decoupling capacitance, which I added a 220 and a 470. Now it doesn't oscillate anymore. It actually works very well. Volume control is done through a potentiometer with a logarithmic taper. So it's a smooth volume control according to our perception. And the way that I decided to build this was through a construction technique called Manhattan construction. So what this involves a regular copper-clad board, but the interconnection of the components is done above the board. That's why it's called Manhattan construction, because it's done, kind of in the air. What you need to do is you need to use a metal hole punch and punch holes in another piece of copper-clad board, thinner, and you have those pieces. And then what you do is you superglue those pieces onto the copper-clad board, and you make the interconnections on those pieces. And for ground connection, you would solder right to the copper-clad board. These are the phases of construction. I initially started with building the audio amplifier, and I tested it, and it worked. It didn't oscillate, and I'm still not sure why, but it did not oscillate. I constructed the IF strip. The IF filters and amplifiers are generally referred to as the IF strip. I constructed the IF strip and the detector and the AGC. I input a RF signal, an amplitude modulated test signal, into it, and I got a tone. And that meant that the IF strip worked. So I could continue on. If it didn't work, then I would have to fix whatever problem that there was. So then I added the RF circuit, local oscillator, and mixer, and I mounted the antenna. This is one of the paintbrush handles from one of the sponge brushes over in the other room. I cut it, put a notch in it, and I put the antenna in the notch, and I secured it with a zip tie, and I glued it onto the board. It actually works very well. And this picture here is what it looked like after I aligned it. Typically, in the radio industry, when you build a radio receiver and you have to set a coil form in place, you would use beeswax to set it in place. So part of the alignment process was you had to move this coil form along the ferrite loop stick until you got maximum signal. And once you do, then you would drip beeswax on the ends of it to set it in place. That's an old ham radio trick that I learned. Now, once it's assembled, it still has to be aligned. See, those tuned circuits, like in the TRF set, they still need to be tuned and peaked. Well, with a super heterodyne set, you only have to do this once. So what I did was I input a test signal, and I attached a scope probe to the audio output. And what you look for is the most perfect, closest sine wave that you can get at maximum amplitude. And what you do is you start with the IF filter, the IF transformer closest to the detector, peak it, and then you go back, and then you repeat the process to get it as peaked as possible. Now once that's done, which that is very important, then you move on to the frequency tracking and frequency coverage alignment. Now, with frequency coverage, what you do is you input set up your signal generator to transmit two test frequencies at the edges of the band. So I did 530 kilohertz and 1680 kilohertz. And I fashioned a loop of wire and I put it close to the antenna for maximum coupling. And what I did, remember I talked about the beeswax and the setting the coil form to set the lower edge of the band, to align that to the so when you would tune it all the way down, it would be at that point. I had to move the coil form back and forth for maximum amplitude. And the reason is, at lower frequencies, the inductance of the antenna has more of an effect. At higher frequencies, it has very little effect. And also for the higher end of the band, there are two little trimmer capacitors in the back of the tuning capacitor, and they allow you to trim the capacitance if you need to. And what you do when you align it, you align it, change to the top edge of the band, and you adjust the trimmer for maximum amplitude. And then the last part is the local oscillator, and they have it's actually very similar, but the local oscillator has to track 455 kilohertz above the received RF frequency. Always has to do that. If it does not, then that signal will get cut off by the IF filters. So very similarly, this is the red slug is the adjustment for the lower portion of the local oscillator, and there's another trimmer on the back of the tuning cap to adjust the higher end of the local oscillator. And once you adjust it, you adjust for maximum amplitude, and that's it. And it's ready for use. And that's all I have. Are there any questions?
How long do you think this took you, like, total to, like, meet?
It took me about probably about maybe 7 or 8 hours straight to assemble, and another hour or two to align. That was it. Wasn't too bad. Anything else?
When you mentioned the gauging before, is that just like another word for connecting it up? Like connecting all the wires together? Or ganging?
Ganging means to gang means a mechanical linkage. It's mechanically connected.